I'm going to talk to you today about some work we've been doing on neuromorphic computing. And just before I start, I just wanted to present my personal biases. So my group has built microprocessors before. We've built FPGAs before. We've built a number of different systems. And when you try to build a system that actually runs something useful, it turns out you learn a lot about why conventional systems are built the way they're built. And there are a large number of costs that we tend to ignore that suddenly come up and overwhelm everything, all the great work you did in optimizing a certain piece of your architecture. And that's kind of why I titled this full stack co-design for neuromorphic systems. And perhaps I should have said toward full stack co-design for neuromorphic systems, because I think that's really an important way to go. So, and here I'm looking at large-scale neuromorphic systems. So, I mean, you're all familiar with this, but I just want to show you, talk you through some of the things you have to worry about in these large-scale neuromorphic systems. We know that there are we have models of neurons and synapses in hardware. They could be analog or digital. They can have simple versus complex dynamics. People have had lots of very public fights about what's the right way to do things, right? We can argue about this to death. There are lots and lots of different, we all know that there are a very large number of synapses for neurons. And so the sort of the dominant factor in any sort of architecture has to do with synapses rather than neurons, just because there's so many more of them, right? Most of these large-scale systems tend to use digital communication between the different parts of the architecture, because that's the main way we know how to do things reliably. It may seem that it's perfectly fine to drop spikes and things of this nature. And you can do that and get things to work. But then the difficulty that really arises really shows up when you try to run something in a repeatable way, right? Because then all of a sudden things are no longer reproducible. It becomes very difficult to develop things on a system like this. So digital and reliable communication has pretty much become the standard in terms of how these systems operate. We've got rough complexity numbers of millions of neurons, billions of synapses, tens of billions, and a huge amount of fan out. And this pretty much kind of forces you into a certain style of communication, because there's basically no choice. We just don't have enough wires. If anyone in the audience is a chip designer, I mean, this is like motherhood and apple pie chip design. I mean, a normal digital chip is massively wiring limited. And just for calibration, an average digital chip has a wiring fan out of roughly 3, okay, rather than 10,000. So if you're completely wiring limited with a fan out of 3, you can imagine what would happen with a fan out of 10,000. I mean, it's just completely impossible. And pretty much, even the very, very early work in this space immediately switched to basically what is packet switch networks. I mean, AER is just another way to talk about packet switch networks, right? So there's just basically no choice, okay? Maybe there's an interesting substrate that, where you can grow the wires and things like that. I've seen papers on this, but, I'm still waiting. Now, my cartoon view of a neurosynaptic core essentially is this very simplified picture. I would argue that most architectures out there, and I'll use Loihi as an example, or True North, or Braindrop, or even Spinnaker at some level of abstraction you can view like this. Essentially has some piece of hardware that's responsible for neurons and synapses and computation. It's got digital I/O for spike communication, and then there are essentially the communication infrastructure that's used to route the spikes to multiple destinations and so on and so forth. Right? All the architectures essentially have this at this level of abstraction. They all look very, very similar. And depending on which architecture you look at, one of the things I should point out is as soon as the architecture becomes programmable, okay, and if you're used to a CPU, by the way, a neuromorphic system is really not programmable, right, by the same level of flexibility of a CPU. But even if we restrict our domain to neuromorphic systems with graph-based computation and think about programmability even in that limited context, as soon as you have programmability, the cost of your system goes up dramatically, okay? So, I mean, and this is well known for any chip designer. Okay, so if I had an ASIC and I compare that to an FPGA, it's a very, very simple, poor man's proxy for, what happens with programmability. You're easily few orders of magnitude blow up in various metrics are just, no problem at all. Okay, 100x, 1000x, these are not big factors when you look at what happens when you immediately put programmability into the mix. And the same thing happens in neuromorphic architectures, okay? Which should not be a surprise. It's the cost of flexible communication is extremely high. So as soon as the system becomes large, the communication costs basically take over. I mean, I was involved pretty heavily with the True North project, and people always ask me, why isn't your neuron analog? Because at least before that project, that was pretty much every neuromorphic system had analog neurons, analog synapses. And it turned out the answer was, I mean, maybe surprising to some of you. It was because it didn't matter. Okay, could have been analog, could have been digital, wouldn't have had, might have changed a very small percentage of our overall system budget. Okay, and as soon as you look at that, then you go, well, then I'm going to do it digitally because in 28 nanometer, I know how to make that work. And in 28 nanometer, making good analog electronics is a non-trivial, very, very high cost endeavor, right? So then the solution is just use digital, not because digital is necessarily better, but because in the overall system, it makes a such a small effect that other considerations now come into play, like, am I likely to get a working chip the first shot? Or, do I have the budget for a respin? Actually, we didn't. Okay, so we didn't really have much of a choice. So, and just to complete the sort of my cartoon view of a large scale neuromorphic system, there's some array of these cores that you just try to stamp out something in a replicated way with some overall network topology. Here I've shown, a mesh network. Everybody seems to be using a mesh network. There's a good reason for that. I don't want to get into sort of religious debates about what's the right network architecture in this audience, but mesh works just fine. And we know how to make those really well. So that's what everybody's sort of system level architecture looks like. So I started this talk by saying I care about full stack neuromorphic systems. And the purpose for this is we need to take all the costs into account. There should be no place for the real cost to hide. I need to make sure that I have some computation that I want to run, and I want to be able to run it on my system and measure everything, right? So for example, some of the benchmarks that were done very early on in the True North evaluation, people were like, well, we can beat your power by a huge factor by this new core idea or this new device and things like that. And I had to point out that, well, half my power on that benchmark was actually switching the pads of the chip, right? Which has nothing to do with the computation. It's just getting data on chip. So, if you can find a way to make that even 20% better, I mean, you'll put everybody out of business. So so having to count for everything is really important. I mean, there's a really funny picture. I should have brought it with me. Of one of the early demos that was done for True North, where we had an IR camera where you could take a picture of the board to look at what was hot. And what was hot on the True North chip is sitting there, sucking 60 milliwatts, 70 milliwatts. Didn't really matter because the power of that board is completely dominated by the FPGA to talk to the IOs, right? So who cares that you've got this great chip? It could be zero, it would make no difference. So these are the sort of things that actually matter when trying to get some system to be used or deployed. So that's what I mean by taking everything into account. It's really important. And this is So I should mention that there's a reason we don't take everything into account, right? This is hard. It takes a lot of work. You're not writing papers. Your grad students are not going to conferences and presenting their work because they're sitting there trying to get everything working. And there's a reason people work this way. But the unfortunate reality is, without having at least some sense of what all these costs are, it's very, very easy to spend a lot of effort on a problem that doesn't actually move the needle eventually. So that's kind of why I'm trying to emphasize this. I mean, my group has written some neuromorphic papers, but we don't write many papers. That's because my students are like, is 20%, but of that, about half of that is a routing table lookup. So the total compute on this chip is like 10% of the system power budget, right? So it doesn't really matter. You can make that 0 and you'll get a 10% improvement, right? So your beautiful new, extremely well-engineered device, great, 10%, right? The other 90%, nothing happened. And it's just sad. This is why, semiconductor industry is doing what it's doing, right? Anyway, so I'm going to run out of time. So I just want to highlight one trade-off that you have to worry about. So dense memories with co-located compute with nice dedicated wiring, right? Remember, as the communication costs are really high, and that's why in True North, we kind of try to build everything as dense as possible and build this fully populated crossbar for local connections. The problem is that's a sharing constraint, right? Any of you who've tried to use the chip knows that it's actually a pretty horrible sharing constraint. Okay, it's really, really hard to utilize that sort of connectivity very effectively. It's much better to go to something much more programmable, which is what the low-E, different generations of low-E have gone through, right? Much easier to use. That comes with a much higher cost. You look at the low-E numbers, they're roughly the same as the True North numbers if you just look at, big picture, but they're in a technology generation that's much, much better. Okay, so they basically took that, they said it's still worth it because that's the right decision. And they probably had to do that because they ran a bunch of benchmarks and realized otherwise I can't utilize them, right? So, but you can't do this sort of trade-off without designing the architecture, doing these iterations, trying to map algorithms. How do we go about doing this, right? And it's nice to see, I haven't been at NICE for many years, but it's really nice to see that there are many frameworks that are coming out that people can use, at least on the software end, high up, to try to raise the level of abstraction at which you can describe these networks. I mean, the Sandia Fugu framework is one of them, and we're looking at that, for example, as a starting point. And I mean, you could go much higher than that, but that's at least a great start because it's better than not having anything else to do. But that still sort of leaves you with the problem of, what about the architecture? What about the hardware? What happens if I add this extra feature to the hardware? What's that going to do? How do you figure that out? So we are trying to do some work. There's the routing tables. No, forget about this. I have pictures of these chips because I worked on them. So, so if I look at the way you go from algorithms to the hardware, you've got some algorithm. You turn it into some sort of network graph, which talks about neurons and synapses and connections and weights, and you might tune those weights at runtime. That's fine. But then you have to sort of map that to the physical realization of the architecture, right? So there's some array of cores, the neurons and synapses and connectivity have to be mapped in a certain way. And actually this mapping matters, okay? So if you do a bad job, you can easily change your power envelope by an order of magnitude, okay? Just to give you some numbers you can't ignore. So you have to do a good job with the mapping and and do that. And that's kind of what we did when we built the True North chip. So what we need is a platform where we can change the hardware. We can then look at the effect of that on the algorithm, update the algorithm, and then hopefully iterate. And this needs an algorithm that's parameterized in a nice way, which is what the Fugu is kind of trying to do that, which is really great. But we need a hardware design that can be modified and that's tunable. And we need a way to get a sort of a real estimate of what the system cost is going to be, right? These are the kind of things that you need to be able to do this. So how do we go about doing this? Well, we've sort of taken a stab at this. This is something my group has been working on for a while. Since my group works on asynchronous design. For those of you who think chip design is hard, at least there are tools that help you. There are no tools that help you to design an asynchronous chip. Actually, there are plenty of tools that help you get it wrong. You can talk to a lot of, I can point to lots of, well, let's not go there. So we actually spent the last 4.5 years building a new chip design flow for asynchronous circuits. So we have a hardware description language and design automation tools. I call it a new hardware description language. It may be new to some, but it's actually ancient. It's based on the first message passing programming language, which was called CSP, invented by Tony Hoare in the 70s. It can allow you to describe the chip at different levels of abstraction at a very high level behavioral message passing program, like a parallel algorithm. We have the data flow representations, the signal level representations, gate level representations, as well as circuit level representations. And what's more useful is you can take sort of characterized results from a very low level of abstraction, like spice simulations of your circuits, and back annotate all the way up to the behavioral, and then you can run your models at that level of abstraction and check and get all the metrics you care about. For the lowest level, we've integrated our simulation framework with Zeiss. So we use the spice simulation from Sandia, and these are all open source tools. They're freely available. You can download them. So this flow is up and running. We've taped out many chips with these, about half a dozen chips with this flow. They work, okay? And this flow is actually an evolution of the tools that we use to design both True North and the brain drop chip, and start a company and a bunch of other things. So lots of different, they've been used for a while. So we basically picked a sort of a very sort of simple event-driven neuromorphic architecture. By the way, the event-driven nature is important for message passing, for global efficiency and power in these neuromorphic architectures. That's actually why most of these have asynchronous communication networks. That's the best way to get that efficiency. So you can have local clocks anywhere you want. That's not a problem. But globally, you really do want this event-driven communication. If you don't, at least our estimate when we did various projects was you lose about a factor of 4 or 5 in power, okay, which is pretty big. We're trying to design the architecture so there are sort of clear interfaces, so you can swap in different components, okay, and use them for doing various things. So what I thought I should do is I just show you. I actually have this on my computer. Okay, so here's the hardware description language. There are parameters, so I can sort of set the grid size. I can change how many neurons each core supports. I can change the fan out size, all of this stuff. And I mean, I can actually even run this. And you can run this, and in the log messages, it's running 10 simulation ticks. There's your 10 barriers in Loihi, if you like. And there's like log messages, just you can see some synaptic updates, all of this stuff. There are learning rules built in. There are various types of synapse types. You can change how much the bit width of any parameter you want. You can change the neuron model, okay? And by the way, the chip I just simulated is roughly the size of Loihi 1. Okay, so it's fast because we're running it at a much higher level of abstraction. Okay, but you can back annotate and get all the right energy metrics. And if you want, okay, you can't really see this, but this is actually a simulation model that you could map to an FPGA and run it. Okay, we've done this with this particular architecture. So you can run this on an FPGA, for example. And we can take, let's see. So the input to this looks like some JSON file, which is essentially tells you how many simulation ticks you want to run, what's happening in every core, what are the neurons, and what's the connectivity, right? So there's a text file you can do. And so we have tools for like various examples. We generate this JSON file. And then there's a little program that generates a file like this. That file contains the programming packets that you would have to inject from off chip to set up all the state of the chip and then run. Okay, that's basically what's happening. So each of those lines is a single packet that you inject to program various memories on the chip. And yeah, so I mean, this works on our FPGA boards and things like that. So that's kind of what we're trying to build up to. Well, I mean, we've got stuff working, but there's still quite a bit of work to be done. Right, so we have a sort of a abstract hardware, you want to go from an abstract hardware format. So the next thing that we're trying to do is raise the level of abstraction even further, right? So right now, when you have a map design, it says this core has these neurons and here's what they do. Okay, but your original algorithm didn't care about cores. So we actually have a tool for we are working on right now. Actually, it's based on the tools that we did to build the chip that we can use to then add those mapping directives. And hopefully we should have, I think probably by the next month, something that'll take the output from something like Fugu and then generate this JSON file, and then you can be able to, then you can play around with more algorithms and see what happens, okay? So that's kind of what I wanted to share with you today. This is what we've been working on. We're trying to put this model into the public domain at some point. I mean, one of my students will hopefully write a paper and then we'll put it online. Okay, that's usually what we're waiting for before putting things in the public domain. We did that in the other way before and it was not good. Let's just leave it at that. Luckily, I know enough people that I got calls from various people who were reviewing a paper and saying, isn't this your stuff? But anyway, you don't always get that lucky. But that's kind of what we've been building towards. So we're trying to build from the hardware up and looking at all the work in this community, building sort of software frameworks. It would be great to have them sort of meet in the middle. And hopefully that'll allow us as a community to have something that's completely open source that we can all work with and try our ideas out and then try to get an evaluation in context. So you count everything. Because without that, I think it's very, very difficult to make real progress. And it's very easy for, the issue today, I think, is somebody shows this great example of an algorithm that's running on a neuromorphic architecture. And somebody doing it in a conventional way can very easily dismiss those results on a variety of different metrics. And we need to get away from that if to have some impact. So that's kind of what we've been trying to do. So with that, I think I'm out of time, so I'm going to stop, and I will be happy to take any questions.